How generative AI empowers materials designers to explore a wider design space, optimize material properties, and expedite the discovery of new materials. Generative AI has the potential to revolutionize materials design by enabling materials designers to explore a wider design space, optimize material properties, and expedite the discovery of new materials. Generative AI models can generate new candidate chemicals, molecules, and materials, and expand both the discovery space and the creativity of scientists. These models can accelerate early materials ideation processes by 100x. By leveraging AI algorithms, researchers can efficiently search and analyze databases containing a wide range of material properties, enabling the discovery of new materials. Generative models can also be used to predict ever more complex properties such as energetic materials, solid-state materials properties, and even the structure of proteins. The use of generative models can predict material properties, minimize the time and cost of laboratory testing, as well as optimize critical manufacturing processes. Who are the major players in the field of material design using generative AI? According to the search results, there are several major players in the field of material design using generative AI. Some of the top companies in this field include IBM Corporation, Google DeepMind, OpenAI, Cobotics, Matter, MIT's Materials Project, and Schrödinger. However, it is important to note that generative AI is a rapidly evolving field, and there may be other companies and organizations that are also making significant contributions to this area. What are some examples of generative AI being used in material design? Generative AI has been used in material design to accelerate the discovery of new materials, optimize material properties, and explore a wider design space. Some examples of generative AI being used in material design include generative flow networks, GFN, generative adversarial networks, GAN, and crystal diffusion variational autoencoder, CDVAE. GFN is a generative model that leverages ideas from reinforcement learning to improve sample diversity, providing a non-exhaustive search of the chemical space. GAN is used for efficient sampling of the vast chemical design space of inorganic materials, and CDVAE is capable of generating two-dimensional, 2D materials of high chemical stability. Some of the top companies in this field include IBM Corporation, Google DeepMind, OpenAI, Cobotics, Matter, MIT's Materials Project, and Schrödinger. Generative AI can predict material properties, minimize the time and cost of laboratory testing, as well as optimize critical manufacturing processes. How does generative AI help in the discovery of new materials? Generative AI has the potential to revolutionize materials design by enabling materials designers to explore a wider design space, optimize material properties, and expedite the discovery of new materials. Some examples of generative AI being used in material design include generative flow networks, GFN. GFN leverages ideas from reinforcement learning to improve sample diversity, providing a non-exhaustive search of the chemical space. Generative adversarial networks, GAN. GAN is used for efficient sampling of the vast chemical design space of inorganic materials. Crystal diffusion variational autoencoder, CDVAE. CDVAE is capable of generating two-dimensional, 2D materials of high chemical stability. Graphical networks for material exploration, GNOME. Developed by Google DeepMind, GNOME uses deep learning to dramatically speed up the process of discovering new materials. It has already been used to predict structures for 2.2 million new materials, of which more than 700 have gone on to be created in the lab and are now being tested. Deep generative models. These models encode material structure and/or properties into a latent space, and through exploration and manipulation of the latent space can generate new materials. What are some potential future applications of generative AI in materials science? Generative AI has the potential to transform materials science by enabling the discovery of new materials and optimizing their properties. Some potential future applications of generative AI in materials science include optimizing materials properties. Generative AI can be used to optimize the properties of existing materials, such as strength, durability, and conductivity, by exploring a wider design space and identifying the most promising candidates. Accelerating materials discovery. Generative AI can be used to generate new candidate chemicals, molecules, and materials, expanding both the discovery space and the creativity of scientists. This can accelerate the materials discovery process by orders of magnitude. Designing new materials. Generative AI can be used to design entirely new materials with specific properties, such as high strength, flexibility, or conductivity. This can lead to the creation of materials that were previously impossible to produce. Improving manufacturing processes. Generative AI can be used to optimize critical manufacturing processes such as 3D printing by predicting material properties and minimizing the time and cost of laboratory testing. Creating synthetic data. Generative AI can be used to create synthetic data, which is generated rather than obtained from direct observations of the real world. This can be used to train machine learning models and accelerate the development of new materials. What are the benefits of using generative AI in material design? Generative AI has several benefits in material design, which include accelerated material discovery. Generative AI techniques enable researchers to efficiently explore the vast design space of materials, leading to the rapid discovery of novel and improved materials. Increased efficiency and cost savings. By leveraging AI algorithms and machine learning, generative design tools can automate the design process, explore countless design iterations, and identify optimal design options, significantly reducing time and costs associated with traditional trial-and-error methods. Enhanced material performance. Generative AI can assist in designing materials with tailored properties explicitly tailored to meet the demands of various industries, such as high strength, conductivity, flexibility, or other attributes. Eco-friendly materials. Generative AI can make eco-friendly materials more accessible by researching and creating them with compositions that reduce environmental impact, waste production, or recycling rates. Wide-ranging applications. Generative AI in material science has wide-ranging applications across industries like electronics, aerospace, automotive, health, energy, and healthcare. Optimized designs. Generative AI can be used to design lightweight and structurally efficient components, such as those used in the aerospace industry by iteratively analyzing load conditions and properties of materials. Automation. Generative AI design can help automate certain steps in the manufacturing process, eliminating the need for costly manual labor and increasing efficiency. Parametric design. Generative AI technology allows for design solutions to be easily modified based on changes to input, enabling designers to rapidly iterate on their ideas and create better products in a shorter amount of time. Learning and improvement. AI models are capable of learning over time, making them likely to continue generating high-quality results throughout long-term use, adapting to evolving product requirements.